when we're looking at oxidation states, it all relies on us understanding what oxidation and reduction are. So remember, oil rig will help you with this. So oxidation is the loss of electrons, whereas reduction is the gain of electrons, and that is key. However, at this high level, it's not always easy to see how electrons have been transferred in redox processes, and remember, redox processes are ones where oxidation and reduction occur at the same time. And therefore, oxidation states are a made-up tool made up by us in order to help us identify which species have been oxidized and which have been reduced. And basically, there's a whole set of rules you need to follow. And if you follow those rules, you'll be able to, first of all, work out the various oxidation states, and secondly, work out what has been oxidized and what has been reduced. So to put that into words, oxidation states are a useful tool for allowing us to identify which species has been oxidized and which has been reduced. So here are oxidation state rules, or you could have said our oxidation number rules. It means the same thing. And our first rule you have to learn is that elements which are not combined with other elements have an oxidation state of 0. So let's look at some examples. Oxygen, phosphorus, sulfur as elements by themselves have an oxidation state of 0. For number 2, the oxidation state or oxidation number of any uncombined ion is the same as its charge. So taking sodium ion, for example, its oxidation state will be +1. Calcium, its oxidation state will be +2. So its oxidation state or number is the same as the charge on its ion. Rule 3, the sum of all the oxidation numbers in a molecule is 0. Such as water, carbon dioxide, hydrogen chloride, etc. So the sum of all the oxidation numbers, so that means the individual oxidation numbers here. So the oxidation number of hydrogen and the oxidation number of oxygen, 2 lots of hydrogen plus the oxidation number for oxygen will equal 0. Carbon's oxidation number plus 2 lots of oxygen's oxidation number will also be 0, and so on. NB, linked to this point, we need to consider ions, and we're looking at more complicated ions, so ones which contain 2 or more elements. So I'm going to call that, in a complicated ion, the sum of oxidation numbers is equal to the charge of the ion. So taking the ion SO42-, so the sulfate ion, what that means is if you add the oxidation number of sulfur to 4 lots of oxygen, you'll still have a net charge of 2-. For the nitrate ion, if you add the oxidation number for nitrogen to 3 lots of oxygen, you'll have a net charge of 1-. Next up, a couple of elements which you just have to learn the numbers for. So hydrogen, try and remember that that always has an oxidation number or state of +1. The exception is hydrogen combined as a metal hydride. And here it has an oxidation number of -1. So you must learn that exception. Fluorine is a second element you need to know the oxidation number off by heart, and its oxidation number is always -1. Oxygen now, this is slightly more complicated. It usually has an oxidation number of -2. However, there are a few exceptions. So firstly, in peroxides it has an oxidation number of -1 instead of -2. And secondly, when it combines with fluorine, it has an oxidation number of +1. In order for this to make more sense, let's write the peroxide formula, and that's H2O2. So hydrogen will have an oxidation state of +1, and oxygen in this case, according to our exception, will be -1. By the way, guys, some teachers might have taught you this in terms of which elements are more electronegative. So you treat covalent compounds as ionic compounds. Obviously that method works too, but this for me is the most straightforward thing to do because you just have to learn a load of rules and it will make sure you get the answer right every single time. Anyway, rule 7, looking at chlorine now as the element. Remember that it always has an oxidation number of -1. There is an exception here. So when it's combined with fluorine, it switches the sign of its oxidation number to being positive, and the same is true for oxygen. Now, the number it turns into will very much depend on the compound you find it in, and we will look at some examples to make sure that actually makes sense for you guys. And then the last rule, which is fairly straightforward, and hopefully you remember this from GCSE and IGCSE, for groups 1 to 3, the oxidation number is the same as the group number. E.g., sodium is in group 1, so its oxidation number is +1. We're going to look at ammonia. Now, according to rule 3, the sum of all oxidation numbers in a molecule is 0. We know that overall this charge on the ammonia will be 0. And that's helpful because now we need to work out the various oxidation numbers of both nitrogen and hydrogen. So according to rule 4, we know that hydrogen has an oxidation state of +1. We know that there is no overall charge, so because we have 3 hydrogens, we have a +3 charge. So what must the oxidation number of nitrogen be? Well, it must be -3. Guys, there's just a quick correction I want to make, which is along rule 6, where I said that when oxygen is combined with fluorine, that it has a +1 oxidation state. Indeed, that is correct sometimes, but it can actually be variable depending on the compound it's in. So just if you change your notes and just write positive here, that will make it much better. And it's very similar to what we wrote for 7, so sorry about that. Following on from our oxidation state rules, we need to be able to look at redox reactions and look at the equations and decide what has been oxidized and what has been reduced. So we're going to have our rules side by side so we can refer to them because we'll need to know what the various oxidation states are in order to do these questions. Looking at our first equation, therefore, we've got sodium, which is a solid, oxygen, which is a gas, forming sodium oxide. And we need to compare the various oxidation states of the elements on both sides of the arrow. So starting with sodium, well, according to rule 1, elements not combined with other elements have an oxidation state of 0. So here we know sodium has an oxidation state of 0. Looking at it in sodium oxide, so according to rule 8, for groups 1, 2 and 3, the oxidation number is the same as the group number. So sodium is in group 1, which is why its oxidation number here is +1. Looking at oxygen now oxygen is an element not combined with any other elements. According to rule 1, its oxidation state is therefore 0. And then combined with sodium, so as sodium oxide, we know according to rule 6 that it has an oxidation number of -2. And do check that the overall net charge is 0 on these things to make sure you're doing it right. And now let's just have a look at what's happened with the numbers. So sodium has gone from 0 to +1, which means that it has lost electrons in order to become positive. And because it's lost electrons, according to oil rig, we know that sodium has therefore been oxidized. Oxygen has gone from 0 to -2, which means it's gained electrons, so it has been reduced. And then depending on how they ask the question, you can add a couple more statements. So although sodium has been oxidized, it means it has automatically acted as a reducing agent because it has caused oxygen to be reduced. So you can write sodium has been oxidized, and you can also write sodium acts as a reducing agent. Concurrently, if oxygen has been reduced, it means it's automatically acted as an oxidizing agent. Let's look at a second example where copper oxide reacts with hydrogen to form copper plus water. So starting with oxygen, let's work out its changes in oxidation state. According to rule 6, it has an oxidation state of -2. There are no exceptions here, so we're going to put -2 here. And looking on the right hand side, again, oxygen will have an oxidation number of -2. So here nothing's happened to it. It hasn't been oxidized or reduced because its oxidation state has remained the same. Copper now, well, we know the net charge of copper oxide is 0, so by definition copper must therefore have an oxidation state of +2. And then on the right hand side it exists as an uncombined element. According to rule 1, its oxidation state must therefore be 0. Hydrogen now, hydrogen exists as an uncombined element on the left hand side, its oxidation number is therefore 0. On the right hand side, it exists in water, the net charge must be 0, so that means that each hydrogen has an oxidation number of +1. And now we can work out what has been oxidized and what has been reduced. So copper has gone from +2 to 0, which means it has gained electrons in order to become effectively more negative. So copper has been reduced. And we might as well write the matching statement here, which is that it acts as an oxidizing agent. Looking at hydrogen now, hydrogen's gone from 0 to +1. In order to become positive, it must have lost electrons. According to oil rig, it's therefore been oxidized. And automatically acts as a reducing agent. Let's do a third example now. So lead oxide plus hydrogen forms lead plus water. So starting with oxygen, we know it has an oxidation number of -2. It's found in water. Now again it has an oxidation number of -2. Lead now, we know that lead oxide must have a 0 net charge, which is why lead is +2. Lead on the right hand side exists by itself as an uncombined element, which is why its oxidation state is 0. Lastly, hydrogen. Hydrogen on the left hand side is an uncombined element, its oxidation state is 0. Found within water, it has a oxidation state of +1. And by the way, this is all found within the rules that we were looking at earlier. Now let's work out what's been going on. Looking at lead, it's gone from +2 to 0, which means it must have gained electrons to become less positive. Because it's gained electrons, we know it's been reduced. And we also know that means it acts as a oxidizing agent. Oxygen has remained the same. It has neither been oxidized or reduced because its oxidation number has remained at -2. Hydrogen, however, has gone from having a 0 oxidation state to a +1 oxidation state. In order to become positive, it must have therefore lost electrons, and therefore hydrogen has been oxidized. And as such, acts as a reducing agent. We're now going to put everything together we've just learned in order to use redox half equations to write balanced equations. So in order to balance a redox equation, we need to follow these steps. Firstly, we're going to start by assigning oxidation states to all atoms in the question. That's what we were just doing. Then we're going to deduce what's been reduced and what's been oxidized. And now step 3, we're going to provide the half equation for the reduction process and the oxidation process. And then this will be what's new to you guys, is adding electrons to either the left or right side of the equation in order to balance the oxidation states. Step 4, we're going to add waters and protons, H+ ions, to balance the O, the H and the overall charge. Then we're going to balance the two half equations, so the electrons lost on one side equals the electrons gained on the other side, a little like a simultaneous equation. And then finally, we're going to add the two half equations together to write the overall redox equation. Let's put this all into practice now by attempting the following question. So according to step 1, we need to assign oxidation states to all atoms in the question. So iron over here is quite straightforward. We can see straight away from the charge on the ion it's +2. Now remember, oxygen is assigned an oxidation state of -2. There's 4 of them, which gives us -8. There's an overall charge of -1, which means that manganese there must be +7. Iron over here is straightforward, and again the same is true for manganese. Let's break up our page into 2 to separate out the reduction oxidation sides. Check the oxidation states to see what's been oxidized, what's been reduced. The iron has gone from +2 to +3, so oxidation has occurred. Manganese over here has gone from +7 to +2, so reductions occurred. Write everything down. separating your reduction and oxidation sides. So we are up to stage 2. We've deduced what's been reduced and oxidized. We've assigned oxidation states. We now need to add electrons in order to balance the oxidation states. So for manganese, we're going from +7 to +2, which means we need to add 5 electrons to this side. Iron's gone from +2 to +3, which means we need to add an electron here. Our next step was to balance your oxygen, hydrogens and your overall charge through the addition of water and H+ ions. So down here we can see 4 oxygens on the left-hand side, none on the right, which means we're going to have to add 4 waters to the right. The problem is now that we have 8 hydrogens on the right-hand side, none on the left, so we're now going to add 8 H+ ions to the left. Happily, we have no such issues here because we've got no extra oxygens or hydrogens. We're getting there now, guys. We need to balance the 2 half equations, so the electrons lost on one side equal those gained on the other, like a simultaneous equation. So we have 5 here, only 1 here. So it's really the equivalent of multiply by 5 to this one. So by doing that, we can see now that those electrons will cancel out. And then we just combine everything to get our final equation. So keeping everything on the left-hand side of the equation that was there before. Do write it out nice and carefully. You wouldn't want to introduce errors at this late stage. And then I'm just going to add my state symbols back in. Let's go full steam ahead with another example. Feel free to pause the video in order to attempt this yourself. So I'm going to start by assigning oxidation states. So oxygen is -2. We have an overall charge of -1, which means that that nitrogen there is +5. Copper here is just 0. Nitrogen here is +2 and +2 over here. So let's work out what's been oxidized and what's been reduced. The nitrogen's oxidation state has reduced from +5 to +2, so it's been reduced. The copper's gone from 0 to +2, so it's been oxidized. Let's split it up. So here's where reduction's taking place. Here's where oxidation has occurred. Let's sort out the electrons. So for nitrogen, we're going from +5 to +2, which means we need to add 3 electrons here. Copper's gone from Cu to Cu2+, which means we need to add 2 electrons right here. Now let's check for oxygen and hydrogens. We have 3 oxygens here, only 1 here. So that means we need to add an additional 2 waters. Through the addition of 2 waters, we now have surplus hydrogens here, which means we need to add 4 H+ ions over here. And then handily on this oxidation side, everything is chill. And now we're ready for our simultaneous equation step. We've got +3 here and +2. The common number that both of these go into is 6, which means we need to multiply this equation by 2 and this one by 3. Rewrite it all. And now just cancel out our electrons and rewrite everything again, keeping your reactants to the left. And you will get quicker and quicker at this the more you practice it.